So the divergence theorem, we have vector A over a surface ds, okay, a vector field A over a surface ds, enclosed surface, equals to the divergence of A dv. Okay, so we have also the integral of A dl, Stokes theorem, equals over a closed line, okay, line, equals to the curl of A ds. Okay, but it's very easy to solve these problems. We have just to know to develop our A at a given surface and found ds. The same, we have to know dv depends on spherical coordinates, cylindrical coordinates, or Cartesian coordinates. Then the same for Stokes theorem, we have just to know or develop our dl and ds. So I will show. For example, for the exercise number 5, why they ask to found to evaluate both sides of the divergence theorem in the region enclosed between the spherical shells divided by R1 and R2. So we have for a sphere, the ds, the surface includes the sphere, the ds of this sphere is defined by dl with dl prime. Okay, for the surface of the sphere, we know that r is constant. Okay, so we have r square sine of theta d theta d phi. Okay, this one for example for the spherical coordinate, we did it in the previous session, and we spend a lot of time to explain the different coordinate. Now x dr, dl prime, if you remember, etc. So now we have this ds, the small ds of a sphere. Okay, now at ds1, r equals 1. So it is 1 sine theta d theta d phi. And when we have r equals to 2, so ds2 is 4 sine theta d theta d phi. Okay, the same if we are in the cylindrical case. This is a cylinder. Okay, so in the cylindrical coordinate, for example, for this part, we have d rho, this ds is d rho rho d phi, which is dl. Okay, so d rho, rho d phi. Okay, so we have just to define the ds. Of course, in the direction, in this case, if in each direction depends. For this one is the direction of z. Okay, with the direction of z, if I add a vector ds as vector. Okay, and this one ds, this ds in each direction is, if the surface like this one is the enclosed surface, the ds is always to the outside, from the origin to the outside. Okay, so in the same direction as r. If we have now, like a melon, two spheres, so the first one with r equals 1, r, the direction r is perpendicular to the sphere, the normal to the sphere. Okay, so this one is from the outside to the origin, so with the direction of minus r. Okay, direction of minus r. What about the second one, this one? For the second one, so we have r from the origin, it's like the r from the origin to the outside, so in the direction, positive direction of r. Okay, so for ds1, when r equals 1, we have ds equals this value times r with the minus. Okay, for the second, ds2 is for sine theta d theta d phi in the direction of r, positive direction. Okay, so in this exercise, when we define our ds, it's very, very easy. So we have in the exercise, yeah, where is it? Yeah, so the problem, we said, evaluate both sides of the divergence theorem in the region enclosed between the spherical shells defined by R1 and R2. Okay, so we will use of course, the divergence theorem of dds over the surfaces equals to divergence of A dv. Okay, now we have just to write ds1, okay, and for r equals 1, and ds2 for r equals 2. Okay, ds1, we said that ds1 is minus this one, the first one, okay, ds2 the second one. It's like melon. Okay, so ds1 is minus 1 sine of theta d theta d phi in the direction of r. And what about d at this r equals to 1? They give us d equals to 3r square in the direction of r. Okay, so when we try to develop our d in r equals to 1, d becomes 3 times 1 in the direction of r. Okay, now what about ds1 is, we have r dot r is 1, okay, cos of cosine p of cos of cosine 0. Okay, then we have vector unit dot vector unit. So we have this integral give us minus 3 sine theta d theta d phi. Okay, so the first integral of theta, if you remember, it's from 0 to pi, and for phi is from 0 to 2 pi. Okay, so because we have a half disk, we turn it to pi in order to develop a sphere. Okay, for ds2, now we can develop our integral. We found it like equals to the value, I think, is minus 12 pi. Okay, so the sign becomes a minus cosine with this minus, so it's yeah, minus cosine from 0 to pi give us 2. Okay, d theta minus sine of theta d theta from 0 to pi, so it becomes cosine of theta d theta from 0 to pi, so it is 2. Then for phi from 0 to 2 pi is 2 pi. 2 pi times 2 times 3, so it is 12 pi. Okay, now for ds2, when r equals to 2, ds2 is 4 sine, we said that it's plus 4, we speak about this ds, okay, ds2, so ds2 is 4 sine theta d theta d phi in the direction of r, positive direction. Okay, when we have now our dds equals to d when r equals 2, so it's 3 times d is 3 times 2 square in the direction of r, so d is 12 r. Okay, now we have dds is 12 r, sorry, this r with this r equals to 1 because dot s, but I let it like this, dot 4 sine theta did phi in the direction of r. So this r dot r is 1. Now I have the integral from 0 to pi, from 0 to 2 pi. 12.4 is 48 sine of theta did phi. Okay, so it is 48. This one is 2 pi. Okay, the integral of d phi from 0 to 2 pi is 2 pi. Then for the sine, it's minus cosine from 0 to pi give us 2. Okay, so the result is I think 192 pi. Now ds over enclosed surface is ds1 plus ds2 equals to 192 pi minus this is where is it, the result of the first one? Yeah, the first one. I will do it like this. Okay, first result and the second result. So it's minus 12 pi, so the result is 180 pi. This is so the final result is ds equals to 180 pi. Okay, now we have to find the same result with the divergence of a dv. Okay, so the second method, using the right hand side. So now using the right hand side of the divergence theorem, we have to find the same result. We have d of d dv. What is the dv of the sphere? We know dv is r square sine theta d theta of the sphere, okay, did phi. We explained all of this in the previous session. Okay, now what our d is the same, is 3 r square. D is the vector fields, okay, in the direction of r. So 3 r square in the direction of r. Now what is d divergence in the of d in the spherical coordinate? It is d over r did r square, sorry, of r square d. Okay, d of r square d over did r, okay, plus 1 over r sine theta d of d theta of what? Of sine theta d in the direction of theta. Then plus 1 over r sine theta, okay, d over d theta did phi. Okay, this is the rule in the spherical coordinate. Okay, then we can develop these calculations. In our case, we have d just in the direction of r, so d on the direction of theta and d in the direction of phi is 0. Okay, is d in the direction of r, so it's 0. Then d delta of d is, divergence of d is 3 r square times r square, okay, d over did r 1 over r square, equals to, I put dr times r square, okay, d over did r square, equals to 1 over r square d over dr. So 1 over r square d over dr of r cube. So it is 1 over r square 3 so we have 3 times 4 r cube, okay, equals to r cube with r square. So we have just r, 12's r, okay. Of d dv is 12 r times, what is our dv? This one is dv, okay, r square sine theta d theta d phi. It's 12 r cube sine theta d theta d phi. Okay, now the integral of the sphere, so from of melon, it's not a sphere, it's the part between two spheres, okay, of radius r1 and r2. So the integral from, now we have from r1 to r2, and theta from 0 to pi, and phi from 0 to 2 pi, okay. Then we have sine of theta give us a cosine, minus cosine of theta from 0 to pi. This result is 2, okay. Time dot d phi is phi from 0 to 2 pi, so it is 2 pi. And the last one is r cube. We have 12, okay, and r cube becomes r in the power of 4 over 4, okay, from r1, which is 1, to 2, okay. So this result give us 2 to the power of 4 is 16 minus 1 to the power of 4 is what? So 15 over 4, okay, it's 15 over 4. So the result is 12.2.2.15 over 4. So this one with 4. 15 times 12 is 180 pi. So we have the same result.